Okay, I'm going to go through the acceleration practice problems. And just like last week, you should have already done these or attempted them. So as I go through them, I want you to correct your work in a different color so that I can see where you've made corrections. And then you'll submit that corrected work, and that will count as extra credit towards the UT Quest acceleration assignment, because it's hard to make 100 on that. And so this will give you a little bit of wiggle room if you struggle with a couple of the problems, or if you do make 100, it will give you extra credit on top of that, and it'll help balance out some other daily grades that you might have struggled with. So as I go through these, please just make corrections in another color so that I can see where you did it. Again, this is not, you're not grading your paper, you're not getting a grade, you're just showing me that you have corrected them and you hopefully understand all the problems. So let's talk about this graph, the first graph that you saw. So this is showing us, it says a car, and on the bottom we have time. So we're looking at a 10-second time period, and we can see that at second 0, so when we start recording at the very beginning here, it is going 0 meters per second. So that car is at rest. After 1 second, it has sped up to 2 meters per second. Then it goes to 4 meters per second, 6 meters per second, 8 meters per second, 10 meters per second. So right there, you can tell that that car is speeding up. Every second that passes, it's going faster than it was the second before. And in fact, if we look, every second that passes, it's going 2 meters per second faster than it was the second before. And that is the definition of acceleration. How much your velocity changes from second to second. So in this section right here, without even doing any math, I know that that car is accelerating 2 meters per second every second. And our meters per second squared are our units for measuring acceleration, because they're saying it's meters per second per second. And it's saying how many meters per second is your velocity changing every second. So without even doing any math, I can tell that that car is accelerating at a rate of 2 meters per second every second. But if I want to do the math, because I should know how to do it, I have a couple of options. So I can just look at the slope of the line. So I can simply calculate the slope of the line, because if I have a time versus velocity graph, my slope will always give me the acceleration. And if I look at the overall slope of that line, so I'm going to look at my rise, okay, I'm going from 0 to 10. So my rise is 10. My run, got to look down here, was from 0 to 5. So rise over run gives me 2. That is my acceleration, which I had already determined. If I want to plug it into the formula, I can also do that. The acceleration formula is final velocity minus initial velocity divided by time. So if I look, and I'm just looking at this one little section, this is my initial velocity. This would be my final velocity, or my ending velocity. So my initial would be 0, because it's at 0. My final would be 10, because it's at 10. So if I plug it in, my final is 10 minus my initial, which is 0, divided by my time. And this took 5 seconds. So I'd have 10 divided by 5, which equals 2. So no matter how I did that, I ended up with an acceleration of 2 meters per second per second. So right here, this car starts from rest and then he accelerates. In this little chunk right here, again, the slope of the line tells me the acceleration. The slope of that line is 0. It's a horizontal line. So that would say that my acceleration is 0. I have an acceleration of 0 right there. But I have to be careful, because an acceleration of 0 does not mean that that object is at rest. This car went from rest and then sped up all the way to 10 meters per second. That was at 5 seconds. At 6 seconds, he's still going 10 meters per second. At 7 seconds, he's still going 10 meters per second. At 8 seconds, he's still going 10 meters per second. So he didn't stop right there. All that happened is he maintained that same speed. He's on cruise control. So when you have an acceleration of 0, that object could be at rest, but it could also just be holding steady. And that's what's happening in this case. He's not speeding up or slowing down. Okay? He's maintaining exactly 10 meters per second as his velocity. And then in this last section right here, he goes from 10 meters per second all the way down to 0. So he's obviously put on the brakes and he's stopping. He's going from 10 meters a second down to rest. And so I know that he's stopping right there. He's decelerating. If I want to know his acceleration, I can do any of those things that I just did before. I can look at the slope of the line. So again, my rise, which in this case is going down, I started at 10 and went to 0. So my rise is a negative 10. My run is going to be 2. So I have negative 10 over 2, which gives me negative 5. So that means he's decelerating at a rate of negative 5 meters per second squared. That means every second that passes, he gets 5 meters per second slower. And that makes sense because he's at 10 meters per second here. At the next second, he's right at 5. That means he got 5 less. And then at the next second, he's 5 less again. He's down to 0. Okay, so I think that explanation pretty much answered the questions that follow. But let me make sure you have the exact answers. Okay, so during which time period is it likely that the driver stepped on the brake? Right here. He's decelerating. So from seconds 8 to 10. During which time interval is there the greatest magnitude of acceleration? Magnitude means numerical value. When is his acceleration changing the most? And that's actually this time period also, year 8 to year 10. It's a negative. Negative doesn't really matter with acceleration. All it's doing is telling you if you're speeding up or slowing down. It's a negative value, but he is changing acceleration the fastest, right there. He changes from 10 meters a second all the way down to 0 in a span of 2 seconds. So the magnitude is the best you could also, or the most, I'm sorry. You could also just compare, it was 2 meters per second squared here, it was 0 here, and then it was 5 here. So when it says, where is the magnitude the biggest, magnitude just meaning numerical value, is 2, 0, or 5, the biggest value. And 5 is. Even though it's negative, that's okay with acceleration. It's still bigger. Okay, using the graph, calculate the acceleration between 0 and 5. We did that. It was 2 meters per second squared. The acceleration between 8 and 9, that was negative 5 meters per second squared. And then number 5 wants the overall acceleration between 0 and 10. This problem is, it doesn't seem like it's the right answer when you work it out, but it is. Because they want the overall acceleration. If we are just taking a snapshot of this car and we're looking at what he was doing at the very beginning compared to what he was doing at the very end. So we are looking at the overall big picture. And if we do that, his initial velocity was 0. He started at rest. His ending velocity was 0. He came back to a stop. So when we plug that into our formula, VF minus VI over time, it doesn't matter what time it is, it's 10 here. We have 0 over 10, which gives us 0, an overall acceleration of 0. So when we look at this car's journey from the very beginning to the very end, it actually has an overall acceleration of 0 because he started at rest and he ended at rest. So if you're looking at little chunks separately, you can determine their accelerations. But if we're just looking at it as a big picture overall, it has an overall acceleration of 0 meters per second squared. Okay. Number 6. Most of the rest of these, we're just using the acceleration formula. I'm going to put it over here. Acceleration is final velocity minus initial velocity over time. So when I'm reading these questions, every value, every number that they give me is either going to be an acceleration, a final velocity, an initial velocity, or a time. Those are the 4 things I can choose from right now, the 4 variables that we're working with. So when you're reading, you need to determine each number, which one of those is it? Is it the acceleration, the VF, the VI, or the time? So a bicyclist comes over the top of the hill at 10 meters per second. I see meters per second, and that's how I measure velocity. So I know this is either my initial or my final velocity. Then he accelerates to 20 meters per second, and that's got to be my other one. So one of those is my initial, and one of those is my final. If he first comes over the hill at 10, and then he speeds up to 20, it's pretty obvious that that's going to be my initial, and that's going to be my final. And then it says that he does it in 5 seconds. So that's going to be my time. What is the acceleration of the bicyclist? So I'm just going to plug it into my formula. Acceleration is VF, which was 20, minus VI, which was 10, over my total time, which was 5. So I have 10 over 5, which gives me 2 meters per second squared as my acceleration there. Okay. Now this one. How long will it take? So this is the first question we've had that hasn't asked for us to find the acceleration. This one is asking how long will it take? It's asking for the time. For a car, and there's a typo here. How long will it take for a car should be to come to a stop? Anytime I see the word stop or at rest, I know that something is going to be 0. Either my VF or my VI. I've got to read the problem to find out which one, but something's going to be 0. Okay, so how long will it take for a car to come to a stop if it's traveling at 20 meters per second and then it decelerates 6 meters per second squared? Okay, so it's starting out at 20 meters per second. That's my VI. It's going to end up at rest. So that's my VF. That's my acceleration right there. But since it is slowing down, since it says deceleration, I've got to make that negative. And now I'm going to plug it in, and this is going to look a little bit different because we have the acceleration. And we're trying to find the time. That's our unknown down there. So my acceleration was a -6 because he's decelerating. My VF, I said, was 0. My VI was 20 divided by my time. My time is what I want to find out. Make sure that you're always getting your VF and your VI into the correct spots. It's not always going to be the big number minus the little number. Sometimes it's going to be the other way, and you're going to end up with a negative, which is what you want if the car is or if the object is slowing down. So do not always go big number minus little number. Make sure you're doing final minus initial, whichever that is. Sometimes you will end up with a negative. So I'm going to simplify this a little bit. I know that 0 minus 20 is -20. All right. When I'm solving for time down here at the bottom, I can't do anything with the variable on the bottom of my fraction like that. So to get something off the bottom, I multiply both sides by time. Okay? And then that makes this one cancel out and go away. So I'm left with time times -6 equals -20. So to get rid of the -6, I divide both sides. It's going to cancel out. So I have time equals a -20 divided by a -6. You'll see that your negatives are going to cancel out, which is what you want because we're solving for time. And time can't be negative. So if your negatives don't cancel and you ever end up with a negative time, you've done something wrong. And you've got to go back and figure it out. A negative time would mean you're going back in time. And we don't know how to time travel yet. So as of right now, your time always has to be positive. Okay, when you divide those out, you'll get 3.33 seconds as your time. All right, this video is going to cut me off, so I'm going to stop this one, and we'll do the rest of the problems in the next video.